Thanks, Jay. It's a pleasure to be here. I appreciate the introduction. I appreciate all the organizers for presenting this meeting. It's been really interesting, and I think the topics are really relevant to what we need to think about as far as how to utilize some of the woody biomass in the forest that we have. So today, what I'd like to do is to talk a little bit about biochar in the forest and the use of biochar in the forest. David gave a really nice introduction about biochar and the potentials for agriculture, but I think many of the folks in this room are more interested in what we can do with the woody biomass that we have in the woods to utilize that and to pay for the restoration efforts that we're trying to accomplish. And so that's what I'd like to talk about today and some of the work that we're doing. Before I do that, I should acknowledge some of the collaborators that I have that are working with us. Deb Dumrose and Greg Jones from the Rocky Mountain Research Station, Jim Ocheletta, Cole Maine, Margot Welch, our partners on the ground that are helping us install biochar field studies. Phil Badger and Eric Twomley are working with some mobile pyrolysis units that David introduced a bit. And Woodham Chung and Tyrone Ben are working with Greg Jones as economists. And I've got some colleagues at the University of Idaho. Armando McDonald is a wood chemist responsible for our portable pyrolysis unit, and the other folks, Kristen, Terry, Mark, Dan, and Shan, are graduate students or staff working with us at the Intermountain Forest Tree Nutrition Co-op. We're receiving funding for this work through the USDA Forest Service. Of course, the Forest Service is very interested in ways to restore forests, eliminate some of the hazard fuels, and improve the health of the forest. We've also received biochar from Dynamotive, so that's a group out of Canada. They have a Sequest char product that they're marketing, and we're also receiving from Char King, which is a small startup company in Emmett, Idaho. Okay, a lot of this I think is going to be familiar to this audience, and so I won't dwell on it too much, but clearly there's interest in utilizing forest biomass for hazard fuel reduction and forest health purposes. We'd also like to have the opportunity to produce energy from this material, potentially improving our energy independence and avoiding greenhouse gas emissions and from fossil fuels and whatnot. But we really would like to know what are the ecological consequences of these biomass removal operations or any mitigation that we might like to engage in with biochar, and like to understand if there are any negative impacts of utilizing the forest for energy production or applying biochar to the forest. And so this is really the perspective that we're taking on this study is, can we do no harm with this? We hear a lot about how wonderful biochar is, and I typically like to have trust with verification and try and look at it in an objective way. And so that's really the purpose of our research. We've heard, there's sessions here in this conference about the lack of profitability of hazard fuels, and I don't really want to go into that too much. Some of the figures that we can talk about are it might cost us $60 to $70 a ton to get the material out of the woods. The price that we could get, a good price for biomass, might be $40 a ton. And so then we'd still be in the negative as far as the balance of this operation. And then we have to move the material out of the woods, and that's going to be some amount per ton mile. And so the further we have to move the material, the more expensive it gets. These are some assumptions that we've used to calculate these here at the bottom. I'd be happy to talk to you about those. But one of the things that we always kind of hang on to, or what are some of the other services that we might be paid for this, avoided costs of fire suppression or greenhouse gas emissions, but to date nobody's really paying us for those opportunities, and so the economics are really quite difficult. So what we're interested in is trying to produce a product that might allow us to make this budget balance. As a consequence of this material being lost or having low value, it's commonly just flared in the woods. It's a hazard, but that's a waste of energy, and it has negative consequences. There is, however, some recreation value in burning piles in the woods, apparently. But the consequences are carbon emissions. Obviously, we're releasing all of that carbon back to the atmosphere. We're losing nutrients. There's volatile nutrients that are lost. There's also particulates that are moved from the site. When we pile it, we redistribute the nutrients, and so are we degrading the sites if we're piling and burning the biomass? So potentially, can we use this for sustainable bioenergy? In the U.S., we create hundreds of millions of tons every year, and there's millions more acres that treatments are forgone on just because of these costs and expenses. And can we use this material to meet our energy needs? So, we talk about forestry and hazard fuel removal, reducing nutrients. But if we remove this material for bioenergy purposes, we're also going to be removing nutrients. And the question is, how much nutrients can we extract? Can we do it repeatedly without seeing degradation? There's some examples. I'm seeing my colleague Helga Van-Meegroot in the audience. She talks about the experience in Europe where pine straw was removed from the forest for several decades, and the consequences are really negative for the forest production. So we want to brace against that. So what we'd like is some sort of a extraction process where we might be able to remove the energy from the biomass in the woods and retain the nutrients and some of the positive aspects of the biomass that we expect. So these fast pyrolysis units are a tremendous opportunity. The idea is that we can take this material, these fast pyrolysis units into the woods. We can convert the material there. We can densify the biomass, densify the energy in the biomass into an oil product, and that allows us to avoid the burdensome transport of bulky, low-value biomass. This oil has some distinct advantages over other products. Pelletization is another way of densifying the biomass, of course. But the oil is a substitute for fuel oil. It can be used. It has been used as a substitute for fuel oil, and it can be refined into other products. So my friend Armando McDonald likes to say that we can produce virtually anything out of bio-oil that we can produce out of petroleum crude oil. So it's really got a huge potential. And the thing to remember too is that biomass is really the only source of liquid energy products that we have at this time. So can we take advantage of that? Can we use that material? Can we upgrade it so that it can be dropped into petroleum refineries? And really that's what I think the tremendous opportunity is here. The value of the wood to turn it into a liquid fuel is tremendous. But, and by the way, we have a co-product, biochar. In my view, biochar is not the be-all to end-all. It's a co-product of fuel production. And so looking for pyrolysis technology that optimizes oil production is the main objective. And fast pyrolysis is the way of doing this. Now we've been, we talk about biochar and bioenergy production as a emerging technology, but in fact we've been making charcoal for a tremendous period of time, and we have a lot of very mature technologies for making charcoal. The question is, how can we get an improved high-value product out of it, such as the oil? So pyrolysis, as David mentioned, has three basic products. There's a gas, there's a liquid, and there's a solid. The gas is a syngas. Consists of methane, carbon monoxide, and hydrogen. Very volatile. Bio-oil is this complex mixture of organic compounds, and the biochar comes along as the solid. So biochar, it's nothing that I think it's been rebranded, but it's nothing new to us. We use charcoal all the time. We use it on our barbecues. It's been used since the dawn of civilization. We wouldn't have been able to smelt ore from process metals without biochar. So it's a very ancient and very commonly known product. We use it for filtration purposes in our households and in our industry. Okay, so we can talk about biochar as a soil amendment also. So it has some value there. It contains most of the nutrients that are in the biomass. So if we extract biomass from a location, if we convert that into a char, we've got most of the nutrients that are in there that were extracted from the site in the biomass, and it's got a large amount of carbon in it. So the biochar is a porous solid. We've been hearing a little bit about that. It's got a extremely high surface area. This electron micrograph gives you an idea of the pore size distribution that we can see. You can see the structure of the wood is retained in this biochar. Here are the vessels, and you can see some of the pits in the walls of these vessels. If any of you are familiar with wood anatomy will recognize those. And so you can also imagine that these are quite interesting niches for microbes that David was also talking about. So this carbon is very recalcitrant. It resists decomposition from microbes and has 1,000-year residence times. Many of you are familiar, I know, with wildfire studies, paleological wildfire studies, and how do we know what the recurrence of wildfires is? It's from dating charcoal. So we pull charcoal out of the soil, and we date that, and that can be thousands of years. So this is some Terra Prieta is a really intriguing example, but we have very clear evidence within our forest system, our local forest systems, of the long residence times of biochar. And just by saying that, this biochar is equivalent to what we find in wildfires. So the charcoal we find in our forest systems is biochar. So there's a couple of points in that regard that I'd like to make. Char provides characteristics that we expect in forest soils. So these forest soil systems have been subjected to multiple burns over the millennia. That material is retained for long periods of time, and that supplies some of those characteristic properties of forest soils. So when we suppress fires from these systems, we are also suppressing the input of carbon, of charcoal into these forest systems. So that's something that we need to be aware of as we're restoring these systems. And biomass removal will also eliminate the opportunity for more biochar input, or for charcoal input from wildfires. So if we want to continue to maintain some of these properties that we expect in forest soils that are provided by charcoal, perhaps applying biochar back to the forest site might be advantageous. So if we have these mobile pyrolysis units, we're producing oil in the woods, we're taking that oil out to drop them into petroleum fineries, we have a co-product there in the woods. That's biochar, and we can use that to apply back into that forest system. We apply the nutrients back into the system, and we get some advantage out of the charcoal that we're applying into those forest soils. So what I'd like to do now is to just introduce some of the work that we're doing as we talk about some of the properties of biochar that might be afforded to forest soil systems. So we've looked at what happens when we grow trees that are native to these forest systems in biochar. We use poplar. It's a very responsive tree. We know a lot about the physiology, and so we look to poplar growth. Oh, I'm sorry, that was Kristen McElligott, who has done a lot of this work, and she has recently graduated. Her thesis is available to any of you that are interested in reading it. She has a nice literature review, as well as some of the other work on the soils that I'll be talking about. She and I put in a pilot project with some biochar, mixing it with potting soil in a greenhouse. So just a measure of the stem growth, and biochar or these trees growing in pure potting soil or with various amounts, increasing amounts of biochar. So you can see that as we increase the amount of biochar, the trees really don't respond tremendously to it. Most importantly, there is no growth stimulation. There's a very regular response to this biochar. All of these were fertilized. So that's one thing that's really important to remember is when we see reports of biochars, responsive plants to biochars, those are always fertilized systems. So the biochar is retaining the nutrients in the system and creating greater efficiency use. If we simply grow plants without fertilizer, we don't really see a tremendous response to biochar. It's a fine potting media, however. When we look at tree growth in response to biochar, and we supply biochar in various forest soils, this is a coarse andesol pumice soil from the Umpqua National Forest, or a fine andesol ash cap from northern Idaho, we see very different responses to the growth of the tree in these as we increase the biochar. And these are non-fertilized, so the fertilizer or any of the nutrients are coming from the soils themselves. One, we see maybe a slight increase or no response at all. The other, we see a decrease in response. And so this is a concern. We don't want to go out to the woods and apply biochar and negatively affect the trees. But one thing that we did was also grow these mix sand in with these soils, and you'll notice that when we mix sand in, we see a very similar response to what we see with the char. And so it's likely that we're simply diluting the soil, that we're mixing this in these pots with these very inert materials, either sand or biochar. Okay, so what does biochar do to the forest soil properties? There are three basic ways it affects the physical, the chemical, and the biological. So let's talk a little bit about about that. We were talking about the porosity earlier. The biochar has a huge amount of void space. That void space has opportunities for storing moisture. It creates surface. So I've heard up to 500 meters squared per gram of soil is in the surface of biochar materials, and so that has opportunity for absorbing materials. It also the porosity, the great porosity, and the pore size distribution that we see creates a very low bulk density of this material, and so the bulk density to char is on the order of 0.2 to 0.4 grams per cubic centimeter, whereas soil is above 1. And so if we blend that together, then we can lighten the soil, which has advantages for root penetration and among other advantages. So these physical features that we see also affect water holding capacity, and this is just a standard moisture release curve where we've looked at the soil. This is the coarse andesol pumice soil versus a blend with char and the soil versus char itself. And you can see char has a very high water holding capacity for any given moisture tension. There's quite a bit more moisture than in the char than in the soil, and the blend is somewhat intermediate. And so this is commonly found in coarse textured soils. Fine textured soils that already have a high water holding capacity, we don't see a large effect of char. And so this is a very important feature. Many of our forest soils are coarse in texture, and so we might be able to take advantage of that. Okay, we can also alter the soil chemical properties by adding char, and this is some of Kristen's work where we blended the material either at the surface or worked it in. Of course, the questions of application are being asked here. How do we get biochar out into the forest world? We're probably not going to be able to till it in or inject it with liquid injectors because of the very rough nature and the retained coarse woody debris and other materials that might be on the site. So we're asking the question here, what's the difference between blending it versus surface application? Of course, the carbon concentration is going to be increased by biochar because it's got very high concentrations. We've also seen the extractable ammonium concentration actually decrease in one of the soils that we looked at, but it was basically unchanged in some of the other soils. Well, the char itself has a ammonium concentration of about 20 micrograms per gram. So it's not surprising that it might decrease the concentration of a soil that has a little higher concentration. So these are really just, we're just blending one material with another, and the consequences of that are evident in the results that we're looking at. So there's also important sorption capacities. Both anion and cation exchange capacity occurs with biochar, so we can see that we might capture nutrient anions such as sulfate and nitrate, as well as what we typically think of as organic matter retaining cations in the system. So we also know that this char, we haven't really talked much about aging of char, but recently produced charcoal is what we consider fresh char, and if that's mixed into the soil, it tends to age over time. And it can be mixed with many other things and tends to age. Begins to oxidize, the surface begins to take on more negative charges, and so we can see that by the oxygen concentration increasing in the char. And so over time, the sorption capacity increases, especially for cations. But there's also the opportunity for absorbing or other organic chemicals. And one important example from the literature talks about absorbing allelopathic chemicals in some systems. So, for instance, if we're dealing with an invasive that has allelopathic capabilities, then biochar might be a way of mitigating or helping restore that. And there's a number of other compounds that might be also absorbed. So this is just some work that we've looked at. We often hear about biochar's capability of retaining nutrients from leaching, and this is just some examples where we're looking at these three soils: an andosol, a spodosol, and a mollisol. And the mollisol, we saw a really important decrease in the amount of leaching that occurred when we had this biochar mixed in with or applied to the surface of the soil. So, but with these other soils, we really didn't see that much of an effect. So it depends on the soil that we're working with really controls the response that we see to biochar. Then there's some biological aspects of this that we're very interested in. And a lot of this is from the literature. We see increased microbial biomass, and we can also see that even though there's increased microbial biomass, sometimes there's decreased respiration rates. So we're talking about an increase in metabolic efficiency of the organisms that are in the soil. We're talking about soil respiration and soil microbial biomass, and so the soil itself might improve in metabolic efficiency. Those are not always the case, though. So we can also see increases in organic matter decomposition as measured by CO2 efflux. There's increased nitrification that occurs. I'll show you a little graph of that in a minute. Increased nitrogen fixation, enhanced mycorrhizal colonization. This is just a good example of that Ogawa published a while back of a mycorrhizal spore with hyphae growing from that, and you'll notice the hyphae is exploring the niches that are created by that biochar in the soil. So there are a lot of interest in how these microorganisms are interacting in the soil. We're looking at altered exoenzyme activities, and talk about that in a second. Here's some information on nitrification that Tom DeLuca published, where we see an increase after a short period of time of adding charcoal to a soil that had not seen fire inputs of charcoal for a long period of time. And so the difference between no charcoal and charcoal was evident for that short-term experiment. We talk about soil organic matter as being enhanced, and we talk about sequestration of carbon in the soil. But I think a lot of times when we hear people talk about biochar applications to the soil, they're counting that as 100% increase in char. So if we add char to the soil and it's got these long residence times, then we should be able to count that as all of the carbon in there as sequestering carbon. But this is a really important study that has been disputed by some folks that are proponents of biochar, but I think it's something that we need to take note of. And when we talk about putting charcoal or humus in litter bags in the field, this is a 10-year study where charcoal and humus was put into litter bags, and charcoal was mixed with this material. And if we just look at the humus and charcoal alone, and we determine what the expected amount of degradation would be, this is this lower line here, but in fact we see much higher amounts of carbon emissions from these soils in the mixed material. And so the concern is that when we add biochar and we enhance the microbial population, that we're creating an environment that's favorable for these for these organisms, and they're growing, and they require a food source, and that existing soil organic matter may be degraded as a result of this. And so I think it's important that we understand this. We have a lot more work to do on this, but we need to understand how much to discount that biochar that we're putting into the system as far as carbon sequestration goes. So one thing that we're looking at is exoenzymes. And exoenzymes are responsible, are the process by which microbes degrade soil organic matter. And so we're looking at enzymes that degrade cellulose or chitin or lignin or aromatic compounds. And when we look at that, we put char, mixed char in with the soil, we can see a decrease in the amount of cellulase and chitinase that are produced, which suggests that perhaps they're not going to be degrading as much of that organic matter, or don't have the capabilities. But it's also important to understand that the ability to mineralize phosphorus is also decreased. So this is some real recent information that Dan Smith is producing, and he's got to analyze the rest of his data and write his thesis. So we're anticipating that before next spring. And so we're also, I mentioned, we're also looking at forest site responses to char, and we've got a number of field sites, but those studies are not mature at this point for me to be able to report to you those results. But obviously we're looking for effects on tree growth and soil properties in those locations. So in summary, we can utilize this material to restore locations. If we produce a biofuel, we might even be able to pay for that, or at least come up with some of the expenses of that material. Biochar co-product can be used. It can be used to mitigate nutrient mining from biomass removals. It might be used to improve soil quality and sequester carbon. These altered soil properties are of interest, and I think is very important to keep in mind and keep track of. And we're also going to be looking at how the soil organic matter is being affected by these exoenzymes and microbial populations. So that's what I have. It looks like my time's up, and I'd be happy to answer any questions that you might have. There's one in the back.
I was curious about the last slide that you showed with the picture where they were spreading the char out, and you can see a giant cloud of biochar in the air.
Yeah.
That's carbon going back into the air. Is that
Well, it's not carbon dioxide, it's a solid, and so it's suspended for the moment, and it will fall back down to the ground.
wind blowing or other things like that?
Yeah, it could be left in the atmosphere for some period of time, but at this point we don't have biochar application techniques. That's the most sophisticated biochar application technique that we have to date to use in our research. So that's our approach to doing it. But you're right. I mean, I think we need to look for new and new opportunities for spreading biochar. There is some particulate matter that's involved in this. I'm not aware of any studies that talk about the particulate emissions from biochar application, but that's something that is an important concern. Is it as important as a concern as wildfire emissions? I don't know. Gloria?
Thanks, Mark. I appreciate the presentation. One thing that I've been really curious about, and a number of us have been noodling over, is when Amazonian indigenous people in Africa and Peru, the all different places where we're trying to carry that out. So building the soil, there was this time factor. They were putting a little bit on at a time, we suspect, over a long period of time. And so the role of time and other things that they were adding simultaneously with probably human waste, compost and other residuals. Some of us have been concerned that if you, in our studies, that if you're putting in biochar directly into the soil, without those other compost additives, that it actually initially could draw nutrients out of the soil and hold them and not make the bioavailable plants until it charges itself, so to speak.
Right.
So in your studies, what kind of time span are you looking at, and do you see any suggestion that maybe over a longer period of time that the nutrients then would suddenly either start to be released to the plants and actually stimulate growth or improve growth over a certain time span?
Right, right. Well, although there are some that challenge this, I don't have many graduate students that'll be around for thousands of years. So most of my studies are going to be on the order of a few years, right? Just the nature of the beast, and that's one reason why when we fertilize with biochar, we see a response. It's probably because we're adding a lot more nutrients than the system has initially, and so we're charging the system with nutrients. These forest systems are very nutrient poor, and so that's one of our biggest concerns. Why we're saying we don't want to do any harm by putting this material out there. And so what are the effects of growth? We do know that char ages quite quickly, and we also know that we have to replace our carbon filters frequently, and so that's because they get charged with nutrients. As soon as they're charged, they're going to begin releasing that material too. What the definitive study, you've probably raised a great hypothesis. What kind of studies could we initiate to address that? I think it's a really important research question that needs to be considered. Jeff?
One of your early slides showed you growing poplars in potting soil and into the various percentages of biochar. Did I see that correctly, that you can grow poplars in 100% biochar?
Oh yeah, biochar is a great potting media. I mean, it's been used as a pot. You can buy it at Hummer's. It's been used for a long period of time. And we talk about terra preta. That's pretty neat. The Japanese have been using biochar amendments for growing plants. They're very well aware of its horticultural value.
I just thought it was interesting that you could use it at 100%.
100%, yeah. That's fresh sequenced biochar. It's kind of interesting. It's got a little oily filter surface to it when you mix it in, and it doesn't wet up very quickly, but I had a great picture of Kristen with this big wad. I said, well, you better mix it in, Kristen, and she, it's black up to her arm. But it is a tremendous potting mix.
If you've got any research or been any research done, you've got, we have a vast forest that burns every year. That's charcoal. It burns hot. A lot of times it sterilize the ground. 50, 60 years into the forest of San Idaho, and I go back and I see after 10 years, there's charcoal everywhere.
Right.
It's just kind of in a time pattern. In 1985, the Butte fire was burned for 80,000 acres. That kind of was sterile there for probably a period of 8 to 9 years, but then it comes back with some biochar. We're talking biochar. That's what we got there.
That's what it is. Yep. It's nothing more than charcoal.
Some of them are generating. They all generate trees. There's the time cycle right there.
Yeah, and that charcoal. I mean, you look at a charred piece of wood in the forest, and that's good, that inner core. There's a rind of charcoal around the outside of it, and there's an inner core of.
You go to the 1910 fire, which was a vast fire, which had a lot of records, and you go through that forest right now and pick up a piece of charcoal and look at the whole forest. It's evident, and it all goes back. Your time period, it's how hot it gets, the charcoal, how much is put on it. So biochar is the same aspect of this natural forest.
That's right, and it's just our time perspective. Just like we don't have 1,000-year graduate students, our lifespan isn't 1,000 years. And yet, these are the time frames that these forests and these forest fires work over. And so you leave charred logs there. Many of them are standing. They eventually have to fall before the cellulose that remains in there can be degraded. Then that charcoal gets broken up and mixed into the soil. How long does that take? It takes hundreds, if not thousands of years. And we have wildfires that come along quite frequently that are adding this material to the system. Great. Thanks very much.